Thank you all for coming to this talk. It's a single track conference. We didn't really have a choice, but thank you anyway. And thank you so much for Facebook and Ryan for hosting this awesome event. So my name is Ed Solvay. I'm an engineer at Twitter. And I'm going to be talking to you about scaling the data processing pipeline of the Answers product. So just to give you an idea about what the Answers product is before we talk about how we scale it. So Answers is an offering by Crashlytics. And Crashlytics was a Twitter acquisition that happened about 2 years ago. Crashlytics started out as a crash reporting SDK. So mobile app developers on iOS and Android could use Crashlytics, compile it into their apps. And then when their apps crashed, we would tell the app developers exactly how and when their apps are crashing. So a little bit over a year ago, we were looking at what we were offering to our end users. And we saw that we were telling people exactly how many times their app crashed in a given day. But we realized that that wasn't really enough to tell app developers whether that was good or bad. So for example, if you looked at our dashboard and you saw that you had 100 crashes on a particular day, how do you know whether that's good or bad? If you had 1 million users on that day, that's actually really good, and you probably shouldn't spend too much time on trying to fix those issues. If you had 200 users on a day and you had 100 crashes, it's pretty bad. So you should invest more of your energy into fixing those crashes. So with that in mind, we set out to build a product that also measures usage in addition to measuring when and how your apps are crashing. So the first aspect of using users is computing daily active users. And once we invested the energy to compute daily active users, we also realized that we had a good opportunity to compute other very interesting things about how people are using your mobile application. So in addition to usage, like daily active, daily new, monthly active, we could compute things like retention. So we can tell you out of the people who installed your app a week ago, how many of those people came back and used your app on a particular day. Out of the people who installed your app a month ago, how many of those people came back and used your app. We could tell you how many sessions there were in your app on a given day, what the median session duration is, and so on. So this is what the Answers dashboard looks like today. And I'm going to tell you about some of the challenges that we faced while building this product and how we solved them. So from day one, we knew that the analytics product would have to be scalable. Thanks to the success of our crash reporting product and the ease with which you could enable the analytics product, we knew that as soon as we released it, a lot of people would enable it, and we would start getting a huge flow of data coming in. We wanted to be fault tolerant. We didn't want, we knew that machines fail, humans fail, and we didn't want those failures to impact our dashboard. We wanted to be actionable. A lot of analytics products just present you with a ton of data and require you to use a lot of drop-downs and to navigate the data and to drill into a lot of data and to force the end user to look for the meaningful information in the data. Our goal was to basically provide you kind of an opinionated dashboard that tells you exactly what the interesting data points are for your app. So you could look at those data points and immediately take action. And again, thanks to the success of our crash reporting product, we knew that this would be in thousands of apps across millions of mobile devices. And the last aspect, we wanted this to be real time. Because this ties back to the actionable nature of the dashboard. If the data that we were showing you were stale by days or hours, it wouldn't be nearly as actionable. So we wanted this to be real time, down to measured in seconds. So today, the data processing part of Answers processes 800,000 events every second coming across from all the devices. So just in the few minutes that I've been talking to you, our servers have processed about 15 million events to power the dashboards for those thousands of apps that we have. So given these challenges, how would you start to build a solution that achieves all these goals? So we started with a stream compute layer. So a stream compute layer might look something like this. So you take those 800,000 events that are coming in every second, you put them into a queue, you send that into a stream processing framework like Storm, and then you persist those computations into a database. So this looks eerily similar to what John was describing. We happen to use Storm, Kafka, Cassandra. So thanks for the troll setup, John. And we'll discuss the merits of our choices, and we'll discuss some of the problems with the choices throughout this talk. So yeah, I mentioned that we use Storm for stream computing. It's an open source project. There are other alternatives to it. There's Samza, there's Spark. They're all open source Apache products. We happen to use Storm because when we started doing this about 3 years ago, it was the most mature one of the stream processing frameworks. So throughout this talk, I'd like to use daily active users as an example of the computation that we perform. It's an easy computation to understand. on any given day, and at any point in that day, we want to tell app developers how many people have used their app on that day. So what would this look like with Storm? So you can imagine this flow of 800,000 events per second coming into our servers. And for the purposes of daily active users, there are three pieces of information in each event that are relevant for that computation. One is the identifier of the app. So here we have this fictitious Cannonball app. The other one is the device identifier for the device that actually sent us the event, the device that was active, and then the timestamp at which the device recorded that event. So you can imagine us taking these events and then maintaining kind of a brute force set for each app. So for Cannonball, we started this set, and we put device 1 into the set of seen devices that we've seen for that app. And you can imagine another event coming into our system. Here's an event for the Twitter Android app. And then we do the same thing. We start another set, and we put device 2 into the set for Twitter. And as more and more events come into the system, we just keep updating these sets. So here's another device for Cannonball. We update their set. Then we have another event, another one for Cannonball, and we update their set again. So you can imagine that at the end of the day, all you have to do is you query this set, and you ask it for its cardinality, and you know how many devices used each app. And you can do this in the middle of the day, too. It's real time. You can query the set at any particular point in a day, and it will tell you the cardinality of the set. So there are two major problems with this approach, and I want to talk individually about both of them. So the first problem with this approach is fault tolerance. So a stream compute layer by itself does not offer you very good fault tolerance guarantees. And so machines fail, so any part of that stream compute layer could go down at any point in time. We could lose queues, we could lose the Storm nodes, we could lose Cassandra nodes, we could lose all parts of it. And losing any part of that system could, in theory, cost to data error or data loss. But even worse than machine failures are human failures. As much as we try to avoid deploying bugs to production, inevitably we all do. And those are actually even more common than machine failures. And with a stream compute layer, it's really hard to unwind the results of having a bug out in production. So to give you an example, with daily active users, we store the results of that computation indexed in seconds since epoch. One time, we deployed a bug where we started storing that in days since epoch. And it took us about 20 minutes to realize that this bug was out in production. And during those 20 minutes, we actually did not update any of the values for any of that. As soon as we realized the problem, we deployed a fix to our stream compute layer. And as soon as we did, we started calculating daily active users correctly again. But we had lost that 20 minutes of data. And because this is a stream compute layer, it's really difficult to go back and recover from those 20 minutes of outage. Those events are gone in a stream compute layer. So how do we address the fault tolerance deficiencies of a stream compute layer? So we introduce a batch layer. And the batch layer runs completely in parallel to your stream compute layer. So on the slide at the bottom, you can see our stream compute layer. And we introduce a layer that's completely parallel to this. So we take those same 800,000 events per second, and we archive them to a scalable file store, a persistent durable file store. So at the volume of 800,000 events, there are only a handful of file stores that are sufficiently scalable to meet that demand. So we happen to use S3. So we send these 800,000 events to Amazon. HDFS is another great choice. It's very, very scalable, and it could handle a type of load. So here on the right side of the slide, you see the same exact 4 events that we used for our daily active users computation in a stream compute layer. They've now been archived to S3. And once they are archived to S3, they basically open the door for us to run MapReduce jobs. We happen to use Elastic MapReduce, and we use an open source language called Cascading. It's a higher order abstraction on top of Hadoop. And for daily active users, we run these MapReduce jobs nightly. So every night, we have the whole set of data of the events that came in throughout that day, and we can very accurately compute the daily active user number for each one of our apps. And the huge benefit of this batch processing is that it's durable, it's repeatable, it's fault tolerant. You're operating on a finite set of data. So if machine failures occur during a computation, it's pretty easy to recover from that. You just restart the computation, and then you run it against the same finite set of input data, and in theory, you're going to get the same result every time, as long as machines don't fail during the computation. And in fact, Hadoop has a lot of this fault tolerance built into it. When a computation is happening in Hadoop, if it notices that a node has failed, it will just restart that part of the computation for you. And again, even more important than recovering from machine failures, the batch layer allows you to recover from human failures much more gracefully as well. If you realize that you have a bug in your batch computation, you fix the bug, you know how long the bug has been out in production. You rerun the batch computation against the same finite set of data, and your output has been corrected. So you don't lose the opportunity to fix data in the batch layer. So how do we fit these two layers together? We've talked about the benefits of the two layers. The batch layer provides you with fault tolerance, with repeatability, but it doesn't provide you with real time. And the speed layer does provide you with real time. So the goal for us, and the idea behind the Lambda architecture, is to take the positives of these two layers, combine them, and kind of throw away the negatives of these two layers by letting the other layer compensate for the negatives. So how do we fit them together? So let's say that we want to show our end users a graph of the daily active users over the last 30 days. So here's what the graph might look like on our dashboard. So to satisfy the request for the data for this graph, we'll first query the batch layer. That's the layer that we prefer. We know that it's repeatable, durable, and we'll ask the batch layer for as much data as it has to satisfy this query. And most often, the batch layer will have 29 days of data. Sometimes we'll have 28 days of data. If you query this shortly after midnight, the batch layer hasn't run for the previous day yet, and it'll only have 28 days of data. Maybe the batch layer is delayed for whatever reason. That's totally fine, too. The batch layer will just have 28 days of data. It will return those 28 days of data back to our API. And then the API has logic in it to say, OK, the batch layer just gave me back 28 days of data or 29 days of data. Whatever it did not give back to me, I'll go ask the speed layer for that. And here you can see the two computations, and we stitch them together basically at query time to provide you with a real-time graph that incorporates the benefits of both layers. Oops. Sorry. Sorry about this. Okay, so this is just an overview of the two, of what I was just describing. It's a diagram of the architecture of how we combine the data produced by both layers. As new data comes in, we send it to both layers, perform computations in the speed layer, perform computations in the batch layer. So one thing that I haven't mentioned yet is the serving layer. Usually the output of your batch layer of your MapReduce jobs isn't immediately consumable by end user queries. For us, the output happens to be data in S3. So we have to take that data in S3 and pump it or transform it into an index database that allows us to basically make it queryable. So that's where the serving layer comes in. And then at query time, we query that serving layer with the batch results, and then fill in the gaps with the data from the speed layer. So I mentioned that there were two problems. And the first problem was fault tolerance. The other problem with the stream-only approach and the stream computation approach that I described is the size of raw sets. So in our example, we had apps that had fairly low cardinality. But we actually have apps that have tens of millions of daily active users. And storing sets with tens of millions of device IDs in them would become pretty expensive. It's possible that a set of that size would fit in memory on one box. But when we do have many apps of that scale, and basically storing the result of a single computation on a single box for each app is prohibitively expensive. So what do we do? How do we address the challenge of not being able to keep raw sets? So we use something called HyperLogLog to address that. And HyperLogLog is in a family of probabilistic algorithms. And the nice thing about probabilistic algorithms is that they sacrifice a small fraction of accuracy. So you don't get an 100% accurate result, but you get huge benefits in either time complexity or space complexity with probabilistic algorithms. So with HyperLogLog, we gain a huge benefit in space complexity. So instead of taking about 10 gigabytes to store daily active user sets for tens of millions of devices, we can use 4K, store up to 1 billion of devices, and only lose a percentage of accuracy. So it's a huge win for us. So how does HyperLogLog work? So it's this beautiful algorithm that was invented by a professor named Philippe Flageolet about 5 years ago. And the idea behind it is that whatever it is that you're counting has some kind of identifier. And you take that identifier and you hash it. And you hash it to a really, really big number. And then once you represent that number as a string in binary, as a string of zeros and ones, you can look for rare patterns in that number. So in this case, we look for consecutive ones in that number. And the idea is that you continuously do this. You hash the devices as you see them. And you keep track of the maximum number of consecutive ones that you've seen. And if you've seen many consecutive ones, it's likely that you've seen many devices to have seen this rare pattern. And if you've seen few consecutive ones, you probably haven't seen that many devices. So another way to think about this is if, let's say you have a friend and she tells you that she's been flipping a coin for some part of the day, but she doesn't tell you how long she's been flipping a coin. All she tells you is the maximum number of consecutive heads that she saw while flipping that coin. So if she tells you that she saw 3 consecutive heads, you'd probably guess that she hasn't been flipping that coin for very long. But if she told you that she saw 20 consecutive heads, you'd probably guess that she spent a good fraction of the day flipping that coin over and over again. So that's exactly how HyperLogLog works. It looks for these rare patterns and just keeps the maximum occurrence of that rare pattern. And that's how it can save so much space. So there's one problem with that approach that I just described. What if that first device that you see happens to be an outlier and happens to have a really rare pattern in its hash representation? That would really skew your estimate. So the way that HyperLog deals with that is that instead of using the entire binary string to look for the pattern, it actually takes a few bits in the beginning of that pattern and uses those to bucket the device identifiers, or whatever it is that you're counting. So just by taking a few bits, you can create hundreds or thousands of buckets. And then each device fits into one of these buckets. And then you take the mean across, the estimate mean across all these buckets. So if you happen to see that weird outlier initially, it would only skew the estimate of one of your buckets. And when you take the mean, that would dampen the effect of seeing this weird outlier initially. So by combining both of these tools, the Lambda architecture and probabilistic algorithms, I mentioned HyperLogLog to you. We use Bloom filters as well. It's also in the family of probabilistic algorithms, and it's used to keep track of duplicates of devices that you have or have not seen. Count-min sketch is another probabilistic algorithm that has similar characteristics. So by combining these two techniques, you can build nice, reliable dashboards that are also 100% real time. So just to give you an idea of these, this is going back to the daily active users example. This is a monthly daily active users view. And you can compute expectations for daily active users for any given day for you. And then as those expectations are not met, we can highlight them and then tell the app developers in real time as those expectations, those missed expectations happen. We can alert them in real time and tell the developer that, hey, your daily active users looks suspiciously low today, or awesome, it looks really high today. We can perform dimensional analysis. So again, with daily active users, we can slice the daily active users by the particular build of your app, and in real time give you comparisons of different builds of your app. So we can tell you at a build level, what is the stability of that particular build, what's the median session length of that particular build, and as you release builds of your app, this data will keep getting updated in real time. So as soon as you release a build of your app to the App Store, we'll start getting data for that particular build, and in real time, you can compare it to other builds of your app. And we can do similar things by other dimensions as well, by the OS that the app is running on, or the device model the app is running on. So basically, in summary, we use these two layers and the probabilistic algorithms to achieve all of this. And again, with the Lambda architecture, we take the real-time nature of the speed layer, and then we compensate its lack of fault tolerance by using a batch layer. And just another computation that's cool. Using these same exact techniques, we can tell you exactly how many people are in your app right now. So we can give you this nice 24-hour logarithmic graph. So the graph is logarithmic because it gives you the most context for the most recent time of how many people are actually using your app right now. So if you're interested in this, I would recommend the Big Data book by Nathan Mars. Nathan Mars is an engineer who coined the term Lambda architecture maybe 3 or 4 years ago. All of the technologies that I mentioned are open source: Storm, Hadoop, Cascading. There's another one that I didn't mention. Hummingbird is a technology that's open source by Twitter. It allows you to write code just once. So in my examples, we actually wrote code multiple times. We wrote a piece of code for the speed layer, then we write it again for the batch layer. But Hummingbird allows you to just write one piece of code, and it will actually take care of running that same piece of code both in the speed layer and in the batch layer. So thank you very much. I think I have 30 seconds for maybe one question. No, so yeah, the question, to repeat the question was that HyperLogLog might be less accurate with low counts. I don't believe that's true. I think because of this mean and then taking the mean across buckets, it dampens the error, the skew. If you look at any there's a paper, academic paper for HyperLogLog, and they actually show you the graph, and it's not super skewed to the low end. It's pretty consistent.